Let's keep going and look at what the surfaces look like in spherical coordinates, because this is going to be a little bit trickier than it was in cylindrical coordinates. That said, the easiest one of all is a sphere, right? Because we know that x squared plus y squared plus z squared is rho squared. So basically we're saying, hey, rho squared is equal to c squared, which means rho is equal to a constant. And that's what a sphere is, right? A sphere, when you think about it, is saying, hey, the distance from the origin is always set in stone at some constant, right? So that is the formula for a sphere. Spheres look like that in spherical coordinates. Right? And I wanted to show you this in Maple. So if I set my coordinates as spherical, right, that's how you do it, it's just a constant. If I just say like, hey, 5, it assumes it's rho equals. That's how it works. So it's like, okay, 5, here you go. Here's a sphere of radius 5. Knock yourself out, right? Because if the coordinates are spherical, that's assumed. Now, what about a half spherical cone? Oh, the work on this is more trouble. Okay, so this would be z equals c times all this mess. But z is rho. And actually, I want to make sure I draw a cone in here so that I've got room. All right, so let me draw the cone. There we go. There it is. Okay, so rho cosine phi equals c square root. X squared would be rho squared sine squared phi cosine squared theta plus, I don't have enough room, I don't think, to write it, so I'm going to put it down here. Rho squared sine squared phi sine squared theta, right? So I'm taking the formulas for x and y and I'm squaring them. Oh my goodness. So that's c times, okay, so now if you look, these both have a rho sine squared phi in them. So this is the square root of rho squared sine squared phi. This is rho cosine phi. And then what's left is a cosine squared. If I factor that out, cosine squared theta plus sine squared theta, which should be setting off little bells in your head, right? So what I did was I factored this piece out of both of them. And it left me cosine squared plus sine squared, which we all know is 1, right? Right. Okay, so that's 1. What to do? And then the square root of rho squared is rho. The square root of sine squared is sine. So this becomes rho cosine phi equals a constant times rho sine of phi. So let me divide both sides by rho sine phi, rho sine phi. So over here, all that's left is the constant. The rho's cancel. We're left with cosine over sine, which is just cotangent. So if the cotangent of phi is equal to a constant, that is a cone. I will be honest, that is not how we write it a lot of the time. Because if the cotangent of phi is some constant, phi is the arc cotangent of that constant, which is another constant, right? So phi is equal to the arc cotangent of c, which is equal to some constant k. And that's how we write it more often. So we write it both of ways, though. All right, next, what about a vertical half plane? Okay, so if y was equal to some constant times x, y is rho sine phi sine theta equals a constant times rho sine phi cosine theta. If we divide everything by rho sine phi, because they both have it in common, it would cancel and leave me with sine of theta equals a constant times the cosine of theta. So therefore, the sine of theta divided by the cosine of theta, which is the tangent of theta, is a constant. So if the tangent of theta is a constant, that would also mean, again, theta is the arctangent of a constant. So theta is a constant k. So if we have theta is a constant k, that actually works the same way it did in cylindrical coordinates. It becomes kind of a hinged door, right? At theta, right? So theta equals some constant. Here's your theta. So if theta is equal to some constant, then we have this kind of plane coming out from the z-axis, from the polar axis, in this kind of door hingy fashion. All right, last one, horizontal plane. Okay, so a horizontal plane, we all know what that looks like. It looks like a flying carpet, right? Hanging above, like that. Okay, so in cylindrical, it was easy. You'd just be like z equals constant, done. But z is not what it was, right? So z is rho cosine phi. That's equal to a constant. So nobody really writes it like this. So then they're going to go, oh, okay, so that means that rho is a constant divided by the cosine of phi, which it's fine. That's just a constant times the secant of phi. So there you go. So if rho is equal to a constant divided by the cosine and or a constant times the secant, that's what you're going to use. And actually, we're going to use this one a lot. You might want to star that one because we're going to use this particular one many times. All of these we're going to use, actually. So all four of these. You can rederive them at any point, but this is how they work. And they're key, especially some of these two, because they, well, and the one up there, they're all key because they help us with our limits of integration for when we do our integrals, which will happen soon in another video.